Hello everyone, now let's look at today's AtCoder beginner contest. First, problem A, ABC preparation. So this is an easy problem. We just need to output the minimum of the four numbers. Now let's move on to the next problem. Problem B, smartphone addiction. This is a simulation problem. It is important to note that O, A, I, B, I's, and T, they are increasing, strictly increasing. So the time period can be separated into things something like this. So this is the start, time equals 0, and this is the end, time equals t. And this is the first cafe, call it C1, C2, and so on. So when he's not in a cafe, his battery charge decreases, and while he's in a cafe, his battery charge increases. But the battery charge cannot be larger than the original charge, which is n. So we may have a horizontal line, and then it will start to decrease again. So at any point, if the battery charge is 0, then we can end our simulation and output no. So we just simulate the process. Now let's look at the code. At first, the battery charge is n, and the last time step is 0. So now we enumerate all the cafes. We will have the enter point and the point he leaves the cafe. So first, we will calculate the charge decrease before he enters the cafe. So this is t equals last, and this is t equals ai. So the battery charge will decrease by ai minus last. So now if the battery charge is 0 or smaller, we will directly print no and exit. Then during the stay at the cafe, the battery charge will increase. So first we suppose that there is no limit and let it increase bi minus ai. Then we check if it is larger than n. If it's larger than n, we will constrain it to n. Then we will update the last timestamp. And finally, we should not forget that after we leave the last cafe Bn, we need to hold the phone until time equals t. So we also need to consider the battery charge decrease during the time Bn to t. That's all. We just do the simulation and we will get the right answer. Now let's look at problem C. So we have a bar which has a length L, and we need to cut it at 11 positions. And we have L is larger than 11. So simply we draw a line. Here is 0 and here is L. Since each of the 12 resulting bars must have a positive integer length, so we mark all the integer points between 0 and L. So we know that if the length is L, there will be L minus 1 points. And we need to choose 11 from the L minus 1 points. How many ways are there can we choose the 11 positions? Obviously, the answer is C L minus 1, 11. Or if you are more familiar with this notation is L minus 1, choose 11. And to calculate this, we have the library function con in Python, which is very useful and simple. Now let's look at problem D, stamp. So it is another problem with segments. So we have n squares in a row. You can see here. So this is square 1, square 2, and square n. Now m of those squares are blue, and we have their positions. I'll say this is blue, and this is blue, maybe this is blue too. The others are white. Now we need to paint the squares. So we need to use a stamp with width k, and in one use we can choose k consecutive squares and paint them red. But the k squares do not contain a blue square. So what does this mean? This means actually we must choose from the segments between the blue squares. So we will have the segments. And we need to paint the segments to red. So our goal is to use the minimum number of stamps. So note that we do not need to minimize k. Instead, we need to minimize the number of stamps. So it is natural to think that we need to choose k to be as large as it can be. So how do we choose k? We can look at this sample. So we have 5 squares, 1, 2, 3, 4, 5. And the first and third squares are already painted blue. So now we will have two segments, two white segments. The first has length 1 and the second has length 2. So in this case, how do we choose k? Can we choose k equals 2? No, because if we choose k equals 2, we cannot paint the first segment which has the length of only 1. We will always intersect with the blue square, which is not allowed. So here we will find that our optimal choice of k will equal to the minimum number of all the lengths of the segments. So first we find all the segments, then we calculate the minimum, and thirdly we will calculate the total stamps we will need. And for a segment with length L, obviously we will have L divide k and its cell. We will need this number of stamps for a segment of length L. Then the final answer will be the sum of all these numbers. Here there are some special cases. First, there might be no segments. In this case, we do not need any stamps. Also, there might be no blue squares. And in this case, we can use a stamp which width is n, and we can paint all the squares blue with one stamp. The answer will always be 1 in this case. Now let's look at the code. So the first case, if there are no blue squares, we just output 1. Then we will deal with the segments. First, we consider the leftmost segment. So if this is the first blue square, and it is not 1, so we will have 1 till b1 minus 1. And if this is the last blue square and it does not equal to n, we will have bn plus 1 till n. So the leftmost segment, the rightmost segment, and the segment in the middle. So if there are no segments, then it means we do not need to paint and we output 0. Otherwise, we choose the minimum length of the segments and set it as our k. And we calculate the sum of the stamps needed by each segment and get the final answer. Now let's look at problem E, sequence matching. So we have two integer sequences. Sequence A has a length of n, and sequence B has the length of m. Then we need to make two new sequences by removing some elements. And the new sequences will have the same length. So the cost is the number of elements removed plus the number of pairs that are not the same. So actually this is very similar to the classical problem of longest common subsequence. And the solution is almost the same. We will use a two-dimensional dynamic programming. So suppose we have dp I j, denoting that this is the minimum cost if we operate on A1 to AI and B1 to BJ, and we want this cost to be the minimum. So how do we deal with the transitions? Suppose we have 1, 2, 3, 2, 2, 3. So now first, let's consider something like dp 2, 2. So first, we can remove a number from A. Then it will become dp 1, 2 plus the cost of the removal. And we can remove one from B, which is similar. And the third case, we can go from dp11 to dp22. And in this case, since 2 equals 2, we do not have extra cost. But if we consider dp32, then they are not the same, so the transition will have a cost of 1, because we can see any different pair will cost us 1. And we just implement this logic in our code. So first case, we can discard the last element of A and use dpi-1j. We can also discard the last element of B and use dpi-j-1. And in the third case, we can keep this pair, and if this pair is the same, we do not need to pay the cost. Otherwise, we will pay cost 1. So the final answer will be dpnm. So this is a very typical dynamic programming problem. And if you have done something like longest common subsequences, you will definitely solve this problem easily. And now we come to the problem F. It is a range query, as the name suggests, very typical, very classical. So there are two types of operations. First, we will replace an element with a new value. Second, we will calculate the range XOR from xi to yi. Actually, this problem will be very easy if we make use of the AC library, which is embedded in AtCoder platform default library. We can use the internal library. So if you are still not familiar with this library, I really recommend that you have a look. So this is its GitHub repository. So we can see here. AC library is the official library of AtCoder. And we can look at its document. So there are a lot of use for things, data structures, like Fenwick tree, sec tree, lady sec tree, and some string data structures like suffix arrays. And we have math functions like convolution, like modular integer. We have graphs algorithms like disjoint set union, max flow, min cost max flow, strong connected components to saturation. They are all very useful. And for this problem, specifically, we will need the sec tree library. So it's exactly what we need, because we know that the XOR operation, it has associativity, and there is the identity element, which is 0. We see that 0 XOR x equals x. So we just need to look at how this works. So to construct the sec tree, it's very easy. We need to define the operation, and in this example it's minimum, and we need XOR, and we need to define the identity element. In this case is 0, and we can have our sec tree created. Let's look at the code, which is very short. So first, we do the input, then we create the segment tree. Here we define its operation and the identity element. Then for each query, if it is the first type, we just set the element to its new value, and otherwise we will do the query. Just use sec.prod. And that's all for today's problem. See you next time. Bye.